Next slide, please. This video method to measure double stars does not use the occultation technique, rather use the technique of letting the stars drift across the field of view and using the same equipment as we use in an occultation and using the same software that we use to reduce occultations, we can determine the position angle and separation of the double star system. Now, first of all, some basics. Why do we want to measure double stars? Well, they have a very important place in astronomy. Knowing the position angles and separations allows us to compute orbits. Once we have an orbit, if we can see the stars visually, we can get their actual separation. And with their actual separation, we get their actual distance. And with the actual distance, we can determine the stellar masses very accurately. And of course, the distance helps calibrate the distance scale to the universe, because we know that a certain star is a 60-watt light bulb versus a 100-watt light bulb because we know its distance. We know its actual brightness, its actual luminosity, and hence this is one of the bases for the entire distance scale of the universe. Next slide, please. Now, one of the common methods to measure double stars is the visual method, in which people years ago and still to this day use micrometers. That's a fancy device in the upper right-hand corner. It's got a built-in protractor, and you have an eyepiece. And you look through the eyepiece, you have some sort of a scale. With the scale, you can determine the separation of the two double star components, usually by letting them drift and timing how many seconds per your field of view is, determine your scale factor for your drift. The bottom two diagrams show the Meade astrometric eyepiece has a built-in protractor etched in on the glass along with a scale. And as you can see, you can measure the angle of the protractor and the separation by watching the stars on the various divisions on the tick marks. Next slide, please. And the accuracy of the visual methods is typically only plus or minus 1 degree and plus or minus 1 arc second at the very best you could hope for. The photographic and CCD methods of measuring the position angle of double stars involves, number one, you take an image, then you measure the positions of the double stars in the center yellow with the yellow circles, and also reference stars with the red circles. You perform an astrometric reduction using the red stars as your coordinate system, which you need a star catalog. You compute the right ascension and declination of the components, and from there you compute the position angle and separation. Accuracy of this method is very good, typically on the order of 3/10 of a degree in position angle and 3/10 of a degree arc second in separation. That's with multiple images. Next slide, please. Before the CCD cameras came into play, well, we really are almost done here. Thank you very much. I believe we're on slide number 4. Back up one slide. We're back on schedule. Okay, next slide. Yeah, prior to the CCD cameras, which came into play in the 90s, this is a machine I used back in the 70s when I was in grad school. It's the Mon measuring engine. And it really was an engine. What it is a microscope, and you lay down the photographic glass plate, typically 5 to 7 inches, on that rotating table. And you have your right hand on the X and your left hand on the Y screws. You turn the screws until the star is centered in the microscope, again with some crosshairs. And then you can read the numbers off the screws. There's actually etch mark on the screws. Each little tick mark on those screws is 1 micron, which is a 1,000th of a millimeter. Okay. Now, the more modern measuring engine that we had in our school actually was hooked up to a device which is the size of a desk, which was a key punch machine. Remember those things? And what you do, once you get the position of the star measured, you'd hit your foot on a foot pedal, and out comes a computer card with the position on it. And after about doing that 1,000 times, and that's how many images you get on this plate here with this objective grading, you could do an astrometric reduction. This would take like a week. Okay, that's why my thesis took 2 years. Okay, next slide, please. Video camera methods to measure position angle separation of double stars involve typically stacking images of the video frames to do an astrometric reduction. And the east-west direction would be determined by two widely spaced frames by letting the star drift across the field of view. You'd measure a frame with the stars on the left-hand side of the frame, and then maybe 20 seconds later, take another image, extract it, and compare that to a calibration double star. You'd need calibration doubles to measure this. Without the calibration stars, you cannot derive a position angle, nor separation for your scaling. Next slide, please. Now comes the Nugent-Iverson video drift method. We devised this method 5 years ago after I noticed that the iMovie CSV file also outputs not only the brightness information per video frame and also the aperture information, but also the XY coordinates of the center of the apertures. And I found this out kind of by accident. I've been using iMovie for 5 years, like many of us, and we in the occultation community just missed this. And what happens is, iMovie's screen, when you open up a program, is basically a big coordinate system grid. You've got XY positions of every single frame on those apertures, up to 3 apertures. So when I found this out, that's all I needed to know to determine that I would start measuring double stars. Next slide, please. So with this XY coordinate system information for each frame, we input that into another program called VidPro, which was an Excel spreadsheet that I wrote, to give us instantaneous position, angle, and separation. Now here's a screenshot of iMovie with a double star. 2 frames combined. The double star system's on the left when the drift starts, and all the way on the right when the drift ends. The XY coordinates are circled in the lower left-hand corner of the screen. Most of us have probably missed that when doing the reductions, and it's also copied to the CSV file, which we also see on the right-hand side of the screen as the video progresses. Next slide, please. This is a iMovie CSV file. You've all seen this. On the left-hand column is the frame number, followed by brightness information, aperture sizes, and over on the right, circled X and Y. Next slide, please. And looking at this X and Y, it's in pixels. It's the position of the star in the XY coordinate system grid in the iMovie field of view. And for iMovie, the 0, 0 position is in the far upper left-hand side of the corner, and the final position is on the far lower right-hand position of the corner, such as 640 and 480. Next slide, please. This is my telescope setup, very similar to Ernie's. I have a 14-inch Meade, a Wattec camera, and I also use a Collins image intensifier. It's not owned by NASA. That just helps me get through airport security, that sticker. And the image intensifier is no longer sold, although occasionally you can find some on Astromart, maybe once every 2 years. But I bought mine new from the manufacturer. And the intensifier adds about, I'd say, 3 to 4 magnitudes to the faint limit of your recording system. Next slide, please. This is a video. Well, this should be a video. This should be video number 1. This is a typical double star drift. And while the video is loading, the video we're going to see is that Washington double star catalog 05404 minus 2151. And these 2 stars, which are drifting from left to right, they are magnitude 12.1 and 12.4. Position angle is 151 degrees, and the separation is 9.8 arc seconds. As you can see, yeah, prime focus, just the camera, no Barlow, no nothing. As you can see, there's quite a bit of noise in the background due to the intensifier, which I'm not too concerned about. And the atmosphere makes the position of the stars fluctuate from frame to frame. Okay, next slide, please.
Next video.
Next video. See, next slide. We have 2 more videos to go later on down the line. Okay, this is one of the sheets in the VidPro spreadsheet program. VidPro means Video Drift Program Reduction. That's the catchy name I came up with. The shaded portion in the right-hand lower part of the screen, that is the complete iMovie CSV file. When you run the video on iMovie, you have the apertures over the stars, and then you save it. Well, what you do is you copy the entire file into this program. And once you do that, you're done. You got your position, angle, and separation, which is in the red boxes on the left-hand center of the screen. Next slide, please. Or the orange boxes. And that information of position, angle, separation is copied to the first sheet of the program in that line kind of down the center of the screen for easy copying into a table when you want to make a table for publication. Also, the program will graph the position, angle, separation of the Washington double star catalog values, in this case 1898 on the right-hand side, and the values I did when I measured the double last year, year 2014, and as you can see for this particular double, there's quite a bit of change in position, angle, and separation. As it turns out, this particular double star, the primary star has a very large proper motion on the order of like 0.2 of an arc-second per year. And over 100 years, that's quite a bit of change. Now, the center of the screen here, you'll see a little line that says WDS data just above the graphs. That's where you would input the Washington double star catalog data. That's a one-line copy, paste. And that is input to the program, which copies the magnitudes, the position, angle, and separations, so you can compare your data to the catalog data. Also, that very important declination, which is used for scale factor calculations, is also copied. Next slide, please. So, occultations are few and far between. So in the meantime, since you have the same exact equipment, the same exact software in your computer, every one of you can go out and measure double stars using these techniques. It's actually quite simple. Now, Lie-Moomy's aperture rings, as we know, have 3 rings. You've got a center red-colored ring, and then 2 outer turquoise-colored rings, blue rings. We're not interested in the photometry necessarily, except to determine which is the primary star and which is the secondary star. We're interested in the position of the star, and that's determined by the center red-colored ring. That gives us our XY position. Next slide, please. Now, how does Lie-Moomy determine the position of the center of the star of the aperture? Lie-Moomy has a method in which it determines this by analyzing the brightness of the pixels. It takes the brightest pixel in the red aperture, and that's identified typically near the top of that peak, and it could be more than 1 pixel of that brightness. And then all pixels with brightness of at least 50% of that value are assumed to be part of the star image. That's the black ring and everything above the black ring on the right-hand contour. And then the XY coordinate is simply the center of mass, or the center of gravity, of all those 50% or higher pixels in the image. Next slide, please. And with the XY coordinates of each star for each video frame, it's a very simple matter using elementary mathematics to compute the separation using the distance formula, the old Pythagorean theorem, and some simple math to determine the position angle. Now, when you determine position angle, the program will automatically compute the quadrant based upon which is the brighter primary star. Position angles in double star astronomy go from 0 to 360 degrees. Next slide, please. Now, in order to determine the position angle of the double star, we're doing a drift. Now, the drift that you set up on your telescope may not necessarily go perfectly east-west across the field of view of your video system. Your camera, in other words, will not be perfectly oriented on the telescope so that the drift is perfectly parallel to the bottom and upper part of the camera field of view. It's going to be offset by a certain amount, and that is known as the drift angle. So we need to compensate for this drift angle in order to get the right position angle. So the way we do this, one method is to use this triangle method, in which we, next slide please. We have a triangle that's created, one for each double star component. It's A, B, and C. And it's very simple math here to compute that drift angle. Alpha, it's the cosine inverse of side AB over AC. Again, this is 7th grade math. And we get a separate drift angle for each double star component, and you average them together. Just add them up and divide them by 2. That's the first method of computing the drift angle. Next slide. Me and Ernie, we do not use this method. Instead, we use the method of least squares. Since we have the XY coordinate position of every single video frame for each star, we can use the method of least squares to get the drift angle. So we get 2 drift angles, because each star gives us a separate least squares solution, and we divide them and average them by 2. Next slide, please. And the accuracy turns out to be 2 or 3 hundredths of a degree, very accurate. Now, when we first came up with this technique a number of years ago, we decided to compare it to some stars in the Washington double star catalog. And we chose stars that had no change in position, angle, and separation for over 120 years. So when we measured these doubles on this sheet, 13 of them, we found that the average change or deviation from our values versus the catalog values for these long-term stable doubles was less than 2/10 of a degree in position angle and averaging 2/10 of an arc second in separation. Hence, we felt confident the technique was working, so we decided to move on. Next slide, please. And that's when we got the bug and started really measuring double stars. And thus, to date, for over 1,100 doubles that we've measured together, the average position angle standard deviation is a little over a degree, and the average standard deviation of separation has been about 0.37 arc seconds. The closest separation I've measured is 3.7 arc seconds, and that's on the next slide. This particular frame is a very good frame. Out of this entire video, we can actually see and separate the two double star components. It is 3.7 arc second separation. Not all frames are like this. The stars are flickering and moving as you saw in the video. They'll merge. One will drop out if there's a really big difference in brightness and magnitude between the two components. But this is as good as we've gotten thus far with our current techniques. Hold on a second, Tony. Okay, next slide, please. Now, how faint can we go? Well, I showed you a video with some 12th magnitude stars. Typically with my system and the image intensifier and my observatory located in West Texas, a very good location, I can see routinely down to magnitude 14 and 15 on a regular basis. So those are a very large database of double stars to be measured. I'm altitude of 1 mile. I'm in the mountains of West Texas. There's no lights anywhere near the place. I'm 5 miles from McDonald Observatory. You know, it's good enough for them. It's good enough for me. Ernie's system, he's in southeast Texas, about 100 miles north of Houston. The skies aren't as great. His magnitude limit is about plus 12 without an image intensifier, using his camera and his telescope system. We have the same telescopes, a Meade 14-inch, but I have darker skies, but Ernie's got an integrating camera. Now, I can see magnitude 12 without my image intensifier, but I like using the intensifier because there's a lot of doubles that haven't been measured in over 100 years that need remeasuring, and that's why I go after the fainter ones. Next slide, please. So, can we go any fainter? Well, as you know, the integrating cameras, which are used in occultations, can also be used in double star work. You add the frames together as the diagram shows, and you can get a brighter star image and go fainter. However, in the drift technique, this causes a problem, because if you integrate a large number of frames, say 1 or 2 or 3 seconds, and you want the thing to drift, next slide please, the images are going to streak and jump across the field of view and be nearly impossible to measure with line moving. So there's got to be a way around that. Next slide please. So my colleague Ernie came up with this brilliant technique, which I'll describe. Here's a video example of a 3-second frame integration. In which the stars have integrating for 3 seconds, and then they drift, they jump, they streak. Another 3 seconds, they jump and streak again. You'll see on the video. The 2 stars on the left-hand side, it's not really a double star system, it's just 2 random stars. Now notice I turn up the integration, the stars get brighter, and then I turn off the motor drive, and they start drifting. Notice how everything streaks. You cannot really measure XY positions with this kind of format. The aperture rings will not follow it. Okay, that's it. Yeah, just 20 seconds. Okay, so next slide.
Just for reference, our folks out on the internet are blasting our videos. Well, we are, and we're looking at it through the internet, so I'm not sure what's going on. Some of them are seeing
Yeah. For those of you on the internet not seeing the videos, this particular example, the stars are integrated for 3 seconds and the motor drive of the telescope is turned off and the stars are streaking across the field of view in jumps. That's what we're seeing. Okay, next slide please. Okay, so Ernie came up with a modified video drift method. And using this method, we've been able to measure stars at least down to magnitude 16.9. And in April of this year, we published a short paper in the journal Double Star Observer, this technique. Next slide, please. The technique works as follows. It consists of 2 phases. Number 1, a tracking phase, and number 2, a drifting phase. With the tracking phase, we're going to turn the integration way up on the camera to bring out the faint star in the star system, in the double star system, so you can see it. And the telescope's motor drive will be turned off, so there's no drifting. It's going to be stationary. And we're going to be recording this on video. Okay? The next phase, the drifting phase, we're going to turn down the integration back down to 30 frames a second, and then slew the telescope over in east or west along the right ascension lines only, same declination, to find a brighter star that can be seen at 30 frames a second. That might even be the target star, the primary of this system. And then we let that brighter star drift across the field of view 3 or 4 times. Again, the video is still running. Next slide, please. And then when we're done with the drifting, you turn it off. Now, why do we do this? Well, the tracking portion, as I just mentioned, allows you to see the faint star, and the drifting portion allows you to put the line movie apertures on there and let it drift, and that gives you the scale factor and drift angle. Next slide, please. So the reduction of this technique, when you're reducing the data, here's an example, another video. Now in this particular video, for those of you that can see it, we have the stars integrating on the left-hand side of the screen. They were integrating. Okay, there we go. They're integrating, and we're just holding the telescope stationary. Then I will turn down the integration so that the brighter stars get real faint and basically disappear. Actually, I do the drift first to the brighter star. Oh, that's the wrong video. We want video number 3. Oh, that is right. Sorry, Ted. Okay, so we let the telescope, we slew it over to a brighter star, and then we turn down the integration to 30 frames a second, and now we can still see the star. And then we move the star over to the left-hand side, east side of the screen, and let it drift 3 or 4 times. Again, this is all on the same video. So in the earlier part of the video, we're tracking, and when we're reducing the video, we have the line moving apertures on those 2 stars we can actually track, and just outputting XY coordinates. Now they'll be pretty much the same coordinates, with some slight shifting due to the telescope's misalignment, mispolar alignment, a little bit of shifting from time to time from one integration section to the next. And then we slew the telescope over to a brighter star, and then do the drift. So we're doing 2 line moving reductions. The drifting reduction gives us the scale factor and drift angle, which we manually input, next slide please, into the first version of the line moving reduction of the stationary star system. Remember, the first one we have only XY coordinates only, no drifting, but we have no scale factor or drift angle. So we use this drift portion of the video, and we manually enter the scale factor and drift angle into the stationary portion of the video reduction. We get our position angle separation. Voila. Now during the drifting phase, you're going to get meaningless results for position angle separation, which we really don't care about. We're only after the scale factor and drift angle. Next slide, please. This is sheet 2 of the VidPro program where you manually enter the scale factor and drift angle. It's marked in red for those of you that have a color monitor. For here in the studio here, we only see pretty much black and white. Next slide, please. So it takes a few minutes longer to reduce this particular double star system than the regular straight drift. You're looking at maybe 7 or 10 minutes versus 5 minutes. So what? Now, the advantages of the drift method. Number one, only the component double stars need be seen and measured. We don't need to see any other stars. We don't need any reference stars. We don't need any calibration stars. Now, the modified drift method, of course, requires a third star. Next slide, please. Each video frame in the drift provides a separate position, angle, and separation, which are all averaged. Every video frame is used. No video frames are discarded. Other video techniques, they discard a lot of frames, only pick the best frames, which is fine, to integrate them together to see the stars. But this particular technique, we use all the data that we get. We don't throw anything away. Next slide, please. The scale factors and drift angles are commuted automatically to very high accuracy. And because the system is self-calibrating, you can take the camera off the telescope, maybe add an extension tube, maybe a Barlow lens, put it back on, and you don't need any more calibration. It's self-calibrating for every single drift, because each drift has its own scale factor and drift angle. Next slide. Unlike a CCD camera, there's no dark frames, flat or bias frames, no shielding or cooling of the video camera necessary. Next slide. As I said earlier, each drift is self-calibrating, and the hardware can be removed and put back on. There's no worries, no nothing, just get right back to work. Next slide. The video method I mentioned at the very beginning of the talk, when you stack frames individually, you've got to calibrate each single exposure. If you want to do another video, you got to recalibrate again. You have to calibrate the beginning of your session at the end of your session. This technique is self-calibrating, not to worry. Next slide, please. Standard deviations reflect the realistic errors in the measurements, and those are our own internal precisions, and since they're very, very high systematic accuracy, we believe they are very accurate. There's no star catalogs required, no calibration doubles, no precession needed. Basically, you're measuring the position, angle, separation for the equator and epoch of date, so what you see is what you get. Next slide. And in my opinion, the large number of XY data pairs is unprecedented in the number of data points you get compared to any other double star measuring technique. Next slide. Now the speckle interferometry guys, they're catching up with us, or we're catching up with them. They have several hundred data points per double star system that they measure. Now, if you have a LX200 telescope, there's no need to turn off your motor drive when you're doing the drift. You simply go into sleep mode, put it into sleep mode, and actually the hand control turns off. Then you hit any button to put the drift back on, and you're back drifting again. Tracking again. Next slide. So the conclusions that I can make here is that our drift method is an alternative method to measuring double stars. The drift method provides a high systematic accuracy for separations and position angles, and the technique uses a feature of Live Movie that was previously overlooked. And I've got a web page for the download of the VidPro program. It also explains the technique. It's on pointsource.com. You get it right there. And that's it. Any questions? Terry.
Yeah, I think 4 comparison points I'm curious about. One was time. You have 2 times, one where you use the integration and I guess your hybrid measure, you know, and the other way you did not. 3 minutes versus 17 minutes or something like that, and they have to achieve a measurement. But that's compared to what's the other procedure and how long does it take? What would they be using if they weren't using this new method? And how long would it take to derive the same data? That's the first comparison I'm curious about.
Well, a drift is, say, 30 seconds. Our field of view, we're doing about 0.6 arc seconds per pixel, and a drift across my field of view with my Wattec, no focal reducer, no Barlow, is about 25-30 seconds on the equator. So I can do that and I do it 2 or 3 times, then I'd use my go-to, move over to the next star system, and keep going. So that's how quickly I can do it. Reducing the... if you're doing it, say, visually, you're going to be looking at a star. You can make maybe 5 or 6 measurements per night over several nights, and then you get your position. Well, true. Now, we can also measure over days also, because you don't necessarily have the best weather every time, with steady atmosphere, every time you make a measurement. I've had double stars that are jumping all over the place due to the air cells jumping all over the place. And those nights are just...
How can you see? I was surprised you could see magnitude stars with your method. What were we able to do with Hubble telescope using the other method? How deep can you see?
Well, visually as faint as you can see. With the other video methods, they're probably down to maybe, I'd say, 11 to 12 magnitude. Ernie?
CCD we are approaching the CCD with a radio.
Right. Much cheaper in terms of the cost of equipment.
How do you save on?
A CCD camera may take a 5 or 10 second exposure. With us, that's maybe a 5 or 10 second integration. But there's a problem when you do integrations, and also with the CCD exposure. Just a second, Roger. The actual error in your measurement is hidden because there's a lot of atmospheric motion in the images that accumulate into a single blob of an image. So you really can't measure what it is. But, frame by frame with the drift, we can actually measure atmospheric fluctuations. And to me, my opinion, our standard deviation, standard errors reflect a more accurate error, estimation of error, compared to just a single CCD image. A lot of these CCD people quote accuracies of 0.05 arc seconds, 0.01 arc seconds. I don't believe it. I don't believe it at all. It's not true. It's the accuracy of the scale factor that they're using. It's just a numbers thing. It's not real, because that image is moving around while that image is exposing, moving all over the place. Roger.
Since you have statistical data on position, you can calculate confidence interval. The spread function that the CCD imager gets does not allow him to calculate a confidence interval for his measurement. So he really does not have the ability to calculate accuracy the way you do.
Exactly. We went through that in email. Yeah.
I wanted to ask you if there's anything about automating the procedure. I mean, it sounds like you have to sit next to your telescope to do this. I mean, some way you can just program your telescope to run all night and do this.
Interesting point. The question is, can we automate this method somehow to program the telescope to just do this all night long? Well, the drift has to be started and stopped. I suppose you could come up with some robotic system to do this. Right now, I just sit in front of the telescope and do it. I have a domed observatory. I turn on my $29 Walmart heater, and I'm fine. In the wintertime.
I close the door.
Tony.
So we had a comment from Jerry Bardecker. I have used the basic drip method process, and it's a wonderful and very productive tool. I have proposed using the Iverson Nugent process along with the Recon imaging equipment as a learning tool in Recon educational communities. And then Ted Swift said, pretty soon the school districts will get annoyed that all their teachers are hooked on astronomy and too tired. So it looks like you're already having an impact out there.
We should have patented this thing. I knew that. Yeah, that's true. Anyway, we've been using this technique for 5 years. We've polished it off. We both learned how to use Line Movie with all kinds of iterations and modifications. We use the anchor function all the time. I've done doubles really faint where the secondary is always disappearing, so I've got to use the anchor function. It pops back in just at the right spot.
Yeah, the anchor function lets it jump around within certain
limitations. Exactly.
But when Ern was talking about doing that for an optimization, if you allow it too big of an area, it will jump over with the anchor function.
Yeah. So that was the exception.
Yeah.
And I didn't want to start the argument.
Right. Well, I think that's right.
Now, our next phase of this research as Ernie mentioned at the very end of his talk, is the magnify function. We're experimenting now with the magnify function to even get closer double stars, and we want to put those speckled guys on notice. That,
I did have a question. When you do your measurements, my movie tells you where the center of the aperture is. Are you using the regular aperture control, or are you using the point spread function method? Because my feeling is I tried to track things with my movie point spread function, and it fails. I mean, it doesn't do a very good job of tracking where the star is in real time. But
yeah, I don't use the point spread function. I use the aperture controls. Yeah,
I think
straight aperture. Yeah.
that's the better tool.
And you can adjust the threshold level also, and you can play with it. It also helps. Yeah, there's a lot to learn about Light Movie. It's a very powerful program. And that's it. Yes, Steve.
Richard, you're using a really small field of view, so I'm distortion when we go back to copper. But does your columns intensifier have distortion associated with it? Check to make sure it's middle, bottom, all you say results.
Yeah, there's going to be a distortion no matter how.
Repeat the question.
The question is there any distortion in the field of view when I'm using the Collins intensifier? The answer is probably not. I've measured it and compared it to some standard doubles. And it's not necessarily the top of the field of view, the center or the bottom. It's from one side of the field of view to the other. And then again, top to bottom is one side to the other. Because your distortion, say radial distortion is going to increase as you go outward. Decentering distortion, coma, obviously affects the edges versus the center. These all kinds of distortions and aberrations, which was the topic of my master's thesis. So I know how to model these things. But I'm not quite sure how to model it on a video, going from one side of the field of view to the other, which is why I'm skeptical while using a Barlow lens. I got to think about that. I may need some help on that. I'm open to suggestions. Tony.
Another question, Oliver, I hope I pronounced his name correctly, Close. There are two versions of VidPro on the web page, one for GPS VTIs and one for setups with 30 frames per second. Can this be changed to 25 frames per second for PAL users?
The question is, the VidPro website here has two versions of the VidPro program, one for a 30 frame per second recording rate, one for an unknown recording rate, which is what you use GPS for. The unknown recording frame rate that you have on your camera, such as PAL or another system, I'd recommend using the GPS version of the program, because what you do is you enter the start time off the GPS on the screen at the beginning and the end time of the drift, and that gives you the total time interval of the drift. And then you simply divide by the number of frames, you get your scale factor. So it could be used for any it's explained on page 3 of the spreadsheet. If not, email me. My email's on that page. That same page, and I'll show you how to do it. Yes, Bruce.
Have you rotated your whole optical system 90 degrees to see if there's any y-axis scale factor that's different than x-axis? Note that the CCP is tipped, a couple percent, and you might get a different scale factor.
Good question. The question is, have I rotated the camera, done the drift to determine if there's a change in scale factor? The answer is yes, I've rotated the camera, but there is a change in scale factor in X and Y, depending on the recording method you use. And that's where this Lancoast resize function comes in that Ernie talked about in the previous talk, because these recorders will, through some unknown compression scheme, will change the aspect ratio of the sky when it records onto your video system. So you've got to rechange it back to match the sky. So we're doing very widely separated double stars, over 100 arc-second separations. We're getting widely different answers from the catalog values. Now, the catalog values are not necessarily the best values, but 5 arc-second difference kind of got us scratching our heads. So Ernie devised the AVI Synth script Lancoast resize function to fix this. What we had to do is rechange the format aspect ratio to match the sky. And that took experimentation by trial and error. So it does affect, in other words, the pixels aren't perfectly square, they're rectangular, is what I'm trying to say, on some systems. Ernie.
Video systems, the cameras, most of your cameras, pixels are rectangular, the wider, the taller than on the wide, whereas you have the CCD camera square. And that plays in this whole aspect ratio thing too. That's what we're trying
So here's something to do in between occultations, try to measure double stars. Thank you.
Thank you for that fascinating talk.